title of his talk is 3D microfabrication of precisely aligned freeform microoptics. Jochen, please.
Thank you very much. And thank you to all the organizers for the opportunity to speak today. So the context of this presentation is supposed to be the field of quantum technology, and we have some points of interaction with quantum technology, so I thought I'd make a very brief introduction, although I'm mostly going to be talking about the 3D printing of microcomponents. So the field of quantum technology has several interesting areas of application. We've heard from Bosch about their interest in quantum sensing, for example, to measure currents in the brain. But there's also, of course, the famed field of quantum computing, where in principle, with a relatively moderate system, one could solve computational challenges that are currently impossible for classical computers, like, for example, the simulation of mesoscale quantum systems. Or, of course, quantum cryptography, where two parties can exchange a cryptography key, which is proven to be impossible to eavesdrop on. In all of those cases, you have situations where you have a quantum system in one position and you want to make it interact with another quantum system. That could be the networking of two quantum computers to build a quantum network. That could be the cryptography situation. And in many of those cases, light is used to make those two quantum systems interact, because photons, visible or maybe even infrared, can keep their coherent state even when they are transported over considerable distance. We heard several kilometers just recently. So you can really use light to do this kind of quantum interaction. And often, if you build a system that is supposed to exchange a photon from one place to another, it's actually not just that the photon is generated at the edge and then absorbed at the other edge, but actually you have a place to generate the light, then you have some kind of optical circuit to work with the light, then you transport it to another optical circuit, and then in the end you have a number of detectors to then detect whether there was light and which channel it took, and things like that. And so for this, often these components are built separately and have to be interconnected with one another. And this is the place where our technology comes in and interacts with these fields of quantum technological applications. And so Nanoscribe, we build microfabrication systems, like the one you can see here in the middle, where you can feed the machine a design for a microstructure, and the machine will print this microstructure for you out of a polymer. So you generate polymer microstructures. So this is our business. We develop these machines, we build and sell these machines. Of course, we also participate in some publicly funded research projects, also some in the field of quantum technology. For example, the MilliQuant project together with Bosch and Qant, Trumpf, Daughter, and other groups as well. I may have time in the end to talk a tiny little bit about this, but I'm going to focus on customer publications for most of my talk. So I said you can print polymer systems, and how does this deal with the interchanging of light for quantum applications? Well, you can print microoptics with it. So for example, this is a set of two lenses. The one in the middle here is a little bit hidden, but you can clearly see the one here at the top. And this you can see is pretty small, several hundred micrometers. You can go even smaller. And these microoptics can now be used to better couple light from one chip or one fiber or another wave or whatever, waveguides to another. You can also print waveguides to basically take light from one waveguide and then guide it to another waveguide, or from a source to a detector, or things like that can be printed with the technology. One slide about Nanoscribe. We have been founded in 2007 as a spin-off of the Karlsruhe Institute of Technology, and we have recently opened subsidiaries in Boston and Shanghai, but all the development and all the production, everything still happens in the Karlsruhe region. We have grown to over 100 employees since our foundation, and most of our customers are actually in the academic research area. We've started to go more into industry, but historically, most machines were sold to academic research. So there's a big pool of peer-reviewed research that I can draw from, actually, and many of the examples that I'm going to show are from that. Short introduction on how the technology works. So we use a laser source, and then we have some galvo mirrors that change the laser source so that the beam that is focused here through this microscope objective is steered around inside the field of view. Zooming in a little bit, so the laser goes into the microscope objective. Microscope objective mostly dips into a droplet of UV resin, and now this focal point here is scanned in the plane. And now by polymerizing the liquid resin, we create a solid polymer object. Conventionally, one might expect if you take a UV resin, you will probably take a UV laser and polymerize it so that each photon of this light source has enough energy to start a chemical reaction to cross-link the resin, but that's not actually what we do. We use a technology called two-photon polymerization, and that means that we take not a UV source, but a red or near-infrared source, so that the individual photons don't carry enough energy to do any interaction with the resin. Only if you have such a high intensity of the laser that you have two photons at the same time interacting with individual molecules, you get a reaction. And that means that the polymerization is actually confined to a very small spot around the focal point, which we use as a 3D printing unit. Now we scan around this spot, and thus we call it our volume pixel or voxel, with which we scan now the volume. But let's come to the application. And like I said, I'm going to talk about aligned microfabrication with the application photonic integration. So if you can print with a high precision tiny polymer objects, you could just use them as mechanical coupling agents. And this is actually happening. For example, this publication from 2018 from one of our customers, they have a chip on which they have some photonic components, some photonic waveguides, and they want to couple light into this chip from a fiber optical cable. And this fiber optical cable, from the way that the experiment is built, has to come in from the top. And if it's placed with a sufficiently high precision onto this chip, they have some kind of a grating that then diffracts the light to the side and couples it into the waveguide. But it's not trivial to align this fiber to the system on the chip. And they said, hey, well, one way that we could solve this is to have some mechanical guidance to help align the fiber. And they use the camera that's integrated in their system to find the position where the fiber is supposed to go and print these mechanical guidance helpers, and thus they could position the fiber. Even though the fiber comes in relatively coarsely, it is actually positioned with a precision better than 100 nanometers in the right spot, and thus they could couple their light much better than they would have conventionally been able to do. But like I mentioned before, you can print optical components with it, so why not print lenses to couple the light directly into the waveguide? And this is a nice experiment that shows some of the advantages of that. Another customer publication, here they look at the situation where they want to couple from a fiber into a waveguide that's on the top of a chip, but they want to couple it from the side. So they have the waveguide on the chip, and they come from the side with the fiber, and they're looking at three different situations. They have a fiber on which a lens has been applied. They take a cleaved fiber, but they bring it very close to the waveguide, or they take a cleaved fiber and then they have a printed lens here. It's actually not a very sophisticated lens, just a simple lens that can collect some of the light and focus it into the waveguide. And in this publication, they looked at, they defined the optimal position in X and Y, how to couple most light in. But then they deliberately deviate a little bit from that. They move it a little bit out of alignment, and they measure how much can we misalign it before we hit a certain extra loss. Losses in this case mostly measured in decibels, which is a logarithmic scale, which helps you can just add up losses in your system. You don't have to do any multiplication, so you can just have a loss budget. And they find that with the micro-optic, they have a much wider range at which they can displace their fibers before they hit an extra 1 decibel of loss. So better than a factor of 2 more loss budget than they had conventionally. You can drive this even further and now print complex micro-optical assemblies to really guide the light where it's supposed to go. Now we're back to the situation where the fiber comes from out of plane. So the fiber comes from roughly from the top, and the waveguides are in plane, and they have the situation that they don't just have one fiber, but they have a whole array of fibers, and they want to couple the signal from the whole array of fibers into their photonic chip. And the system that they designed looks like this. They have a lens here, and the lens collects the light and then focuses into this waveguide, which then bends around and couples it into the silicon nitride waveguide here on the chip. And they don't just print one or a couple, but they print many, 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 as you can estimate from this picture over here. And they do this by using a programming interface that's integrated into the machine. They built their own marker recognition and printed it like this. And actually, since we're talking about startups every now and then in the program, this group here, our customer from Münster, have actually founded a startup that deals with this kind of situation, that you want to couple from waveguide fibers into some kind of waveguide situation on a chip, in a cryostat actually, because they want to do quantum technology with it, and this is the method that they use. And this situation, this waveguide and lens combination actually offers a fairly broadband coupling. So if you compare it to other methods with these gratings to couple light from a fiber into a waveguide, actually you are fairly narrow, but they are quite broadband, on which wavelengths they can couple light into this waveguide. Same group, different publication. Now we're actually dealing with quantum technology. We're dealing with single photon detectors. If you want to send a single photon over a large distance, at some point you have to detect this thing. You have to take a single particle of light and generate a macroscopic signal from that. And for this also you need to, of course, have a very high degree of coupling. So here they have the same basic situation. They simplified it to make it easier to print. You still have a lens and a waveguide guiding light into a different waveguide on the chip. But now they've, instead of having a long curving waveguide, they have just added a mirror here. So light goes in, is reflected at the mirror because it's a interface between the polymer and the vacuum or gas has a total internal reflection, and then the light goes here into this waveguide. And in this waveguide, it is picked up by this superconducting nanowire. And superconducting nanowires are an established technology to detect single photons because they can be driven very sensitively close to their superconductive normal state. And thus you can take a single photon, the energy from a single photon, and generate a macroscopic resistance signal from that. And they, in their publication, you should check it out if you're interested in single photon detectors, they compare their technology to other methods of coupling light and detecting single photons, and they find that they have a much higher detection efficiency for a relatively broad band if they compare it to other technologies for this. Okay. Now I'm coming to the second part of my talk, where I'm going to introduce a new system that we've built. All that you've seen has been done actually on our established machine, the Photonic Professional GT and GT2. But for the next couple of minutes, I want to talk about a new machine that we recently launched called the Quantum X Align. And in this machine, we have integrated this whole marker alignment and printing in place into automatic processes. So first example I'm going to talk about is printing on fiber arrays. So now you're just not dealing with an individual fiber optical cable, but you want to do it with many because you want to do parallel communication. You want to interchange several quantum states at once. So you make arrays of fiber cables, and they are typically mounted in such a system. So there's a glass block down here, glass block up here, and there are these V-shaped grooves into which the fiber optical cables are pushed so that they are in a defined position, and then the front is polished, and now you have an array of fibers in defined positions. And with the Quantum X Align, we can now use an integrated camera to detect these fibers in the field of view of the microscope objective. And actually we're using a backside alignment so that the core of the fiber, which is not always exactly in the same place, the core of the fiber is illuminated, and we can detect exactly where the core of the fiber is, and then we can print in place. So now I'm hoping that the video will work. This is always a gamble. And it does, very good. So now you are watching the machine printing live. So this is the luminescence of the resin when it's illuminated by our cross-linking laser. Now we found the V groove here, and this was the light. This is the light from the fiber core, and now we've detected it, positioned the laser exactly on top, and we are now printing a lens directly at this position. And this can be done, of course. Now the machine knows exactly where the next core is coming out, and then it's going to move there and repeat the whole process until the fiber array has been printed on completely. Now, if you're printing coupling optics, you can look at basically several different situations. We're looking at two right now. So either you build a lens deliberately to focus the beam very tightly, to directly couple it into a small opening, for example, a small waveguide on a chip, or you can make a wide beam and then print a second optic to receive light coming from a wide spot. And so in this case, you only need one lens, but you have to position it very precisely. In this case, you need two lenses, but you have a bit relaxed alignment, like I showed in the previous example. If you mismatch it by a couple of microns, you're not losing a lot of light. And we characterized examples of both these situations. Here we are looking at two lenses on fibers in a similar configuration, a similar geometry. So the light is focused to a spot here, 600 microns out, and then from there it diverges again, and it gets into another similarly shaped lens on a different fiber array. And in the bottom situation, we're looking at a tightly focused spot directly coupled into a waveguide on a chip. And we characterized both those situations. And up here, we find that we have a very moderate loss of just 0.7 dB per lens, so 1.4 total, 0.3 dB per lens, of which are actually just reflection losses, which could be combated very easily by coating the lenses anti-reflectively. And then down here, we have been looking at the situation lens and waveguide. And here we have a total loss of 1.7 dB per interface. We were looking at different wavelengths here, but in principle, anything in between would also work. How am I doing time-wise? The clock has started too early. Am I still good on time? Oh, yes. Okay, perfect. So I'll just keep up. Here we characterize this in a little more detail, not just looking at the losses, but also in order to understand if we can properly design lenses and get to the right functionality. We built up some measurement setup. So here we're looking at a lensed fiber array again. And so we looked at the light intensity distribution in this square. So first of all, inside the waveguide, then it looks something like this. And once you get out of the lens, actually the beam, of course, gets, so out of the waveguide, the beam gets wider, and then the lens focuses it again. And I seem to have lost power, so now you have to just follow my finger. Or maybe you have a different, I think the laser is out. Doesn't matter, I'll just keep up, and if you have something more, let me know. So we're basically measuring the shape of the beam when it's left the lens, and thus we can infer how the light was behaving inside the lens as well. And yeah, we did the same, of course, also with the light coming out of this where it's focused tightly, but the same situation. And if you happen to be interested in lensed fiber arrays, we actually have a partnership with a company that's exhibiting here right now, a company called Fix. They deal in fiber arrays and things like that, and through their web shop, you can actually buy lensed fiber arrays that were made on our machines. Great, thank you very much. Everything works again. So, second situation we're looking at is now you have a waveguide on a chip, and here's the chip edge. And of course, in most situations, there are a couple of different alignment markers from the different previous lithography processes that created this waveguide on a chip. and the light's supposed to go in or out along this axis here. And for this, we actually need a little bit more complicated setup, because the chip can be misaligned in all kinds of directions by a couple of degrees, could be rotated, could be tilted, and to be sure that we detect exactly which position and which orientation we need to print at, we have integrated a confocal microscope, meaning that we use the whole printing system as a confocal microscope, and now we can make a 3D image of the environment, and we look at the reflected light, and thus we can now, like I said, detect the position and orientation of the chip, and now print lenses here onto the chip edge exactly with the right position and orientation. And again, we could characterize and see that we understand well how the resin behaves, and that we can predict and match the beam shape that we want to have to couple light from one position to another. So I mentioned we are also doing some publicly funded research projects. So one is that we're still working on is called Handheld OCT, and the idea here is that you have a optical tomography sensor that can look at the inside of an eye and get a 3D image of the inside of an eye to do some medical analysis and some detection. And these devices already exist, but the problem is that of miniaturization. You have a big machine, and people that have problems with their eyes are often not so mobile anymore, and ideally you would like to have a portable instrument. And this is something that we're dealing with in this project, handheld a device for this, and our contribution here is the printing of lenses onto a chip edge where the light can go in and out for having all of this integrated into a small portable package. So we're also participating, I mentioned this before, in the milliquant project for light sources, and here you can see a printed lens actually on the exit of a laser chip that has been fully electrically contacted. So now you can actually get the light that's generated in your laser chip focused and in the direction that you need it to go. Or we also looked at a fiber array to couple here from the chip into the array, and we also characterized this setup here and got to fairly good results. If you're interested in those numbers, talk to me afterwards, I would say. So I come to the summary, and I guess I roughly kept my time slot. So many quantum technological applications require high efficiency coupling of photonic systems one to another, and our technology to photon polymerization allows you to print components on pre-structured surfaces. I showed you some applications in the field of photonic integration, and this is available commercially in the form of the Quantum X Align that has automatic alignment routines integrated. Thank you very much for your attention. I hope there's time for a couple of questions.
Thank you, Jochen. Very exciting as well here. Any questions in the audience? No question. I have a question. You talk about two photon polymerization. You know, having studied polymer chemistry long time ago, it sounds very exciting. But I mean, to just get the probability of two photons meeting, that means you have to have a laser that is pretty highly, what's it called, like a femtosecond laser. So you have, is
Yes.
that, because I mean with a regular laser, you would not achieve those probabilities. Is that
That's perfectly right.
Yeah.
I didn't go too much into detail on that, but that's exactly right. We're using a femtosecond pulsed infrared laser. Otherwise, with the intensities that we have, we're talking about a couple of 100 milliwatts, you would not be able to reach the sufficient two-photon density to get a nonlinear effect like this. But because it's pulsed in femtosecond pulses, we do reach that intensity, and we can use the two-photon effect even at relatively low powers.
Okay. Yeah. Low power, so cold, so it doesn't warm up the system too much,
Yes,
right?
that's right.
Exactly. Okay. Great. Very exciting. Questions? No, I have another one. You know, I'm in the medical field, biomedical field, so the OCT interests me. You talk about a handheld OCT for eye, and the immediate question is, can you do that for skin as well? Because OCT is used in detecting skin lesions as well.
My understanding is yes. I'm not such an expert in the medical applications, but I've seen several OCT publications.
Yeah.
Actually, one was for some kind of endoscope that combines spectrography and OCT in one lens. That was done by another spin-off that uses our technology from Stuttgart. And so I believe if it's working inside the blood vessels, I don't see why it wouldn't also be able to penetrate the skin. So I guess the answer is yes. Once you have this handheld technology, it should be straightforward to port it to other fields of medical applications.
Okay, my last question is on the business model side. I mean, how do you work with your customers, partners? Is this a licensing model, or do you just sell your technology to them?
We're generating our revenue on selling the machines. So we develop the machines and we sell them, install them, and then some customers choose to have some kind of a service contract with us, and many customers choose to buy resins that we produce, but that's not really revenue generating. Most of the revenue comes from just selling the machines.
Thank you very much. Any questions? No? Then let me thank Jochen again. Very exciting. Thank you very much. There's a little present for you here as well. Thank you.
Thank you.